Hi again, and welcome to Lecture 4 in the Galaxies course at Stockholm University. This one is a three-parter. In the first part, we will take a cursory overview of the topic of active galactic nuclei with a specific emphasis on the unification model of AGN. And in the last two videos, we will dive into the world of star-forming galaxies, which is a topic we will be covering more over the next 3 lectures. Beginning first with active galactic nuclei. What are they? In a nutshell, active galactic nuclei are supermassive black holes which are accreting material, mainly gas, under the emission of extremely strong radiation. Active galactic nuclei have higher overall luminosities than normal galaxies, and they also have very different spectra. And another important characteristics of them is that the energy that they emit is far beyond what can be accounted for solely by the mechanism of star formation. If we take a look at the plot over here on the right, we can see for comparison a star formation galaxy spectrum, and we can see the spectra of a type 1 and a type 2 AGN for comparison. I should point out here that the x-axis here is frequency, which is flipped compared to what we're used to looking at in wavelength space, such that higher energies and shorter wavelengths are to the right, whereas we are usually looking at it on the left side of the axis. But what we can see is, well, you should be able to recognize the two humps of the SED of a star-forming galaxy from the last lecture. But we can also see that basically across the board, the AGN is way more luminous than the star-forming galaxy is. This is particularly true in the infrared, where we can see that it is way brighter, and it becomes more true again in the ultraviolet. You can see that the type 2 AGN is a bit fainter than the type 1 in the red end, and once we get into the ultraviolet, the type 2 becomes much fainter than the type 1 AGN. Once we are out in the X-ray and gamma ray regime, we can also see that the star-forming galaxy basically emits nothing there. Star formation cannot produce energies large enough to emit X-rays and gamma rays that in any immeasurable quantity, but AGN can. But we can also see that type 1 and type 2 AGN have quite a different output of X-rays compared to each other. Almost all galaxy bulges host supermassive black holes, but not all galaxy bulges host AGN. And that is because, of course, to have an AGN, it is not enough to have a supermassive black hole. You must also have some nearby gas that it can guzzle up, and in that way give rise to this emission of excess energy. But a minority of these black holes do accrete gas, and they release energy by the E equals mc squared Einstein formula. And given that c squared is a very, very large number, that means that these supermassive black holes can begin to emit very, very large quantities of energy, and they become active galactic nuclei, or AGN. Practical observational evidence for AGN comes in a number of different varieties. The first thing we can see is that in some spectra of galaxies, we see very broad wings of Balmer emission lines, not only of galaxies, also of quasars. We're going to come into that later. But in some of them, we see very broad emission lines, especially in the Balmer lines, but not only in the Balmer lines. We may also see what we would find as peculiar emission line ratios. If we look over here to the right, we see what is called the Baldwin-Phillips-Terlevich diagram, or BPT diagram, which is a little bit like the Hertzsprung-Russell diagram or the color magnitude diagram, in the sense that we are plotting not various colors or color magnitudes, but we are plotting various line ratios against each other. And just like in the Hertzsprung-Russell diagram, we can see that galaxies don't fall randomly over this phase space here. We see that there is kind of what we could call a main sequence of star-forming galaxies here. What we see here is, along the x-axis, the ratio of nitrogen over H alpha, which is from hydrogen. And that is a measure mainly of the metallicity of the gas we're looking at. Whereas up the y-axis, we're looking at oxygen 3 over H beta, which is also to a certain level metallicity dependent, but it is more strongly dependent on ionization, and therefore this is more of an ionization measure. And what we see is usually that a higher ionization follows with, or is coincident with, lower metallicity, and vice versa. That is because metallicity, higher metallicity, makes for way more efficient cooling, and more efficient cooling means lower mass stars in general, which again means fewer and less energetic ultraviolet ionizing photons emitted from these stars. So the higher the metallicity, the less potent the ionizing spectrum from the stars in this region would be. So generally, star formation cannot give rise to what we see out here, which is a combination of high metallicity and very, very high ionization, which means that what we see here is active galactic nuclei, AGN. This diagram here is what we would call the original BPT diagram, as it was devised in 1980. Later on, other diagnostic diagrams of the same kind, where other line ratios are plotted against each other in order to see these different kind of locuses of, or loci of, where star-forming galaxies and AGN and so on are falling, have later on been devised. So we now have like a whole battery, or like a whole arsenal of various diagnostic diagrams we can look at. We still often call these BPT diagrams as kind of an umbrella term, but the original OG BPT diagram is the one that you're looking at here. Another thing that we can see, which is evidence for AGN, is blue compact high energy emission in the nucleus of a galaxy. What we see here is perhaps not a super bright example, but it is an example. We can see that there is very bright emission from the central regions of this spiral galaxy. So these observations here are taken with the Hubble Space Telescope at optical wavelengths. But when we look at it in near-infrared wavelengths or mid-infrared wavelengths taken with the James Webb Space Telescope, we suddenly see that it is much, much brighter. And we could probably also see a stronger emission in the extreme ultraviolet, provided that it is not wrapped in too much dust, and in X-rays. I'm sorry, I have not actually aligned these images very well, but you can kind of see how they are images of the same galaxy in different wavelength ranges. AGN also display strong and unpredictable variability, and that is because other variable objects are typically something like pulsars or Cepheid variables or other kinds of variable stars. And these will typically display some kind of periodic variability, a periodic pattern of variability. But the variability of AGN is unpredictable and unperiodic because it simply depends on nearby gas being caught in the gravitational well of the black hole, being sucked into it and accreted onto the very, very hot accretion disk which is surrounding the black hole. So what we see is basically like a trace over time of the amounts of gas that have been caught in this gravitational well and accreted onto the central black hole. And of course, there is no reason why this would be periodical, because why would the supply of gas coming in from outside to a supermassive black hole be periodical? It will not. As an aside, what we're looking at here in the plot to the right is actually not just only one light curve, but it is multiple light curves from multiple images of the same AGN, which are created by gravitational lensing, which is a topic we will come back to later in this course. What happens there is that a very massive foreground object, I believe in this case it is a galaxy cluster, is bending the light from the distant quasar, and in this process also showing us multiple images of the same quasar. But these multiple images of the same quasar, they are showing us light that has traveled at slightly different distances and therefore also slightly different travel times. In a quasar that is billions of light years away, we might see variations in the travel times and therefore delays in these variability patterns of up like a few months and up to a few years. So fractionally, these are tiny, but they're still large enough that we can measure them. So what we have seen here is multiple different images of these variability curves in the of this quasar that have then been like pushed together and superimposed on top of each other. And you can see that although the agreement is not perfect, there's a little bit of scatter here, it is definitely a very good agreement, which also is a very strong argument that these are indeed multiple images of the same object, because these are not periodical, this pattern is basically as unique as a human fingerprint. Another thing we can observe from AGN are what we would call bipolar radio lobes, as you can see a very beautiful example of here to the right. This is a galaxy called Centaurus A or Kentaurus A. You can see this galaxy we have here with an AGN in the center, and you can see these very high velocity jets of material that are being flung out of the center of the AGN. And you can even see this highly ionized gas, which is being ionized by the shocks of this high velocity gas. So this is like surrounding gas that is being hit at very high speed by these ejecta from the central AGN and creating this like very shocked gas. And these lobes will tend to be emitting quite strongly in radio wavelengths. There's not just the shocks, but also the interaction with magnetic fields, actually mainly the interaction with magnetic fields, which creates the most of the radio emission that we see in these galaxies. So, as you may already have guessed from what I told about before, there are different types of AGN and they can present in very different ways. The first type of galaxies we can look at is what we call Seyfert galaxies, which are defined as a class based on some observational characteristics. First off, they have an extremely bright nucleus. A nucleus then can be up to 10 to the 4 times brighter than the Milky Way nucleus. How bright they are varies by a lot, but 10 to the 4 is a quite nice average of how much brighter they are than the Milky Way nucleus. Another thing that is important for Seyfert galaxies is that you can actually see the galaxy. This is not true for all AGN types, but it is true for Seyfert galaxies. We can look at an example over here where we have the same galaxies with 3 very different exposure times. In the top, we see short exposure where we can basically only see the nucleus. In the bottom, we have a very long exposure time where we can see the entire disk and the entire stellar population. This is a very saturated image, of course, but we can definitely see the spiral structure of this galaxy. This also should give us a hint of exactly how bright the nucleus actually is, that in this image here, we can very clearly see the nucleus, but the actual larger stellar population is basically invisible up here. It is just not bright enough to be visible at such short exposure time. In the central panel, we have kind of what you could call a compromise. You can see that the nucleus is still by far the most bright object here, but you can also begin, if you squint, to see the larger structure of the stellar disk of the galaxy surrounding it. These kinds of AGN are typically found in spiral galaxy nuclei. About 10% of spiral galaxies of type A or B are Seyfert galaxies, so it's actually a quite sizable fraction. Seyfert galaxies come in 2 different subtypes, Seyfert 1 and Seyfert 2. If we look first at Seyfert 1 galaxies, we can see that they have very strong emission lines from highly ionized gas. You can see in the spectrum, you can see there's neon 5, which means quadruply ionized neon. You can see doubly ionized oxygen. You can see 6 times ionized iron, and so on and so forth. You can also see, if you look at the H-alpha line from hydrogen, that it is very broad. It can have a line width, full width, have maximum in velocity space of up to 10,000 kilometers per second. But it also, as you can see, has these narrow components on top of the broad lines, which gives it this funny look, like some kind of funny hat or something. These are also very bright X-ray sources, which is not visible in this spectrum, but they are. And they're also bright gamma ray sources. These things they have in common with Seyfert type 2 galaxies, except that Seyfert 1 galaxies are brighter in X-rays than Seyfert 2 are, but they are about the same brightness in gamma rays. Finally, you can also see the blue bump out here. You can see that it becomes very bright, very far out in the blue and towards the ultraviolet colors. And if you look at the galaxy, a Seyfert 1 galaxy, in the blue and ultraviolet spectrum, you can actually see that this blue bump will outshine the entire rest of the galaxy in these wavelength ranges. For comparison, here is a Seyfert 2 galaxy, where you can see that it also has these strong high ionization lines, although maybe not quite as high ionization as the Seyfert 1 galaxy. It is also bright in X-rays, as the Seyfert 1 galaxies was, but not as bright as the Seyfert 1 galaxies. It is bright in gamma rays, about the same as the Seyfert 1 galaxies, and the continuum is dominated by the host galaxy. You do not see this very strong blue bump that you saw in the Seyfert 1 galaxy, which means that if you look at this Seyfert 2 galaxy in continuum lights, you will mainly see the stellar population of this. It will perhaps be a little bit brighter in the nucleus due to the AGN, but generally the integrated light of the galaxy will be dominated by the stellar component. Some Seyfert galaxies are also in between these two types. You can call them Seyfert 1.5. So even though there is quite a clear, what you say, bimodal distribution of Seyfert galaxies, it is not a completely clear binary distribution. There are in-between types. They are not very common, but they exist. The next type of AGN that we have observed is the radio galaxy. Radio galaxies emit most of their energy actually at radio wavelengths, typically as these long polar jets or lobes that you can see an example of here. You can actually ever so slightly see the source, the AGN itself here in the center, and then you see these very strong energetic jets that are puffed out in each direction. This radio spectrum is non-thermal. It is synchrotron emission from relativistic electrons, which are shot out at very, very large velocity from the poles of this AGN, and then are interacting with the surrounding magnetic field where they're being accelerated as in a synchrotron and emitting synchrotron radiation from this interaction. The spectrum of these radio waves have a power law slope with the luminosity as a function of frequency being proportional to the frequency to the power of the slope alpha, with alpha being somewhere between 0.7 and 1.2 in the lobes and about 0 in the core. These galaxies or these types of AGN are typically hosted in elliptical or lenticular galaxies, often even in CD galaxies, which, as you remember, are also the ones that we call the brightest cluster galaxies, these extremely massive early type galaxies that sit in the very heart of galaxy clusters. Up here, you can see a few numbers which compare the radioluminosity of a radio galaxy to the radioluminosity of the Milky Way. The Milky Way in radio has about 2,500 solar luminosities, whereas radio galaxies will vary between 10 to the 8 and 10 to the 12 solar luminosities. So these are very, very radio bright objects. Here is the same radio lobes, but here shown in their actual environment as it is seen in optical lights through the Hubble Space Telescope, I believe, judging from the diffraction spikes in these stars. You can see the host galaxy here. You can even see that it is a quite massive elliptical galaxy with what looks like a smaller satellite galaxy here, although it could also just be a foreground galaxy, but it could definitely be a satellite galaxy too. But just take a little bit of time to look at how large, how humongous these radio lobes are. They actually go as far as about 500,000 parsecs from one end to the other. So this is comparable to the scale of an entire galaxy cluster. These are very, very large structures and should also give you an idea about exactly how much energy is actually released in these jets. Quasars mean quasi-stellar radio sources. These are extremely luminous AGN which are completely dominated by the light from the nucleus. Often we cannot even detect the host galaxy, and these are basically just point sources when we look at them in optical or UV lights, which is why they're called quasars. Quasars means quasi-stellar or star-like. And originally they were discovered as very bright radio sources. And once they were then observed in follow-up observations in optical wavelengths, basically they just looked like stars. They were point sources. We could not even see the host galaxies. It was then quickly found out that they had what, by the standards of the time in the 1960s, that they had extremely high redshift, which also means, of course, that their distance to us, they're definitely extragalactic objects, not just stars in the Milky Way, and also that they're so distant that because of the inverse square law, they must also be incredibly, incredibly luminous to still shine bright as stars in the sky. So these radio loud quasars are 10 to 100 times more radio bright than the radio galaxies I just described on the previous slide. So these are even another 1 to 2 orders of magnitude brighter in radio than the radio galaxies from before. On the other hand, it was later found that only a small subset of these quasi-stellar objects actually were radio loud. So quasi-stellar radio source kind of became a misnomer, and that gave rise to another subgroup of these objects, which are the QSOs. QSO stands for a quasi-stellar object. It doesn't contain this abbreviation of the radio source. So QSOs are basically the same as quasars, except they don't emit in the radio. They are also extremely luminous, can in the optical be 10 to the 13 or even 10 to the 14 solar luminosities, which means that they can completely outshine their host galaxy to an extent where the host galaxy is not even visible to us, because it is simply drowning in the diffraction patterns of the point source in the center. These also have very blue spectra with strong and broad emission lines. As you can see here, you see the same broad emission lines as in the Seyfert 1 galaxies, except even more extremely so. But you also see that they are very, very steeply rising in intensity towards the ultraviolet end of the spectrum. They also usually have quite high redshift, and their spectra look quite similar at all redshifts. So there doesn't seem to be a very strong evolution in how quasars work, like what physical properties give rise to this extremely bright emission over cosmic time. Quasars and QSOs are, technically speaking, not quite the same kind of object, but I have to say that in practice, they are often used interchangeably, which mainly means that QSOs are very often just called quasars, no matter of whether they are radio loud or not. But if we have to be sticklers, it's actually only the radio loud ones that should be called quasars. So after some time, for a while, it wasn't clear that these different kinds of objects were even the same kind of object. It was only after a while that people have found out that these objects might actually be various visual manifestations, you could say, or various visual expressions of the same physical processes and the same physical properties, just viewed in different ways. So the broad diversity in AGN types and AGN observations, they reflect both intrinsic and apparent variation. Intrinsic variation meaning that the object that we're looking at are actually different, right? These can be variation in like their luminosity, their optical luminosity, their UV or X-ray luminosity, their radio luminosity, and so on. There are such variations. But there are also apparent variations where we look at the same class of objects, but we may look at them from different angles. And that means that certain parts of them might be obscured, so we don't see them. So they look different to us at a large distance, even though they're actually the same kind of objects. So how do we disentangle this? There might also even be variation as a result of evolutionary effects in these objects. So how do we disentangle this? This is where the unification model comes in, and the unification model is perhaps the most important part for you to take away from the whole topic of AGN. This simplifies how we understand AGN by explaining this as a result mainly, but not purely, of differences in viewing angles. So, for example, ionizing radiation might not escape isotropically. It might not be emitted with the same strength in all directions. Something might be obscuring it in some direction and not in other directions, and so on. The active nucleus itself might be obscured or partially obscured, or obscured from certain angles but not from others, and so on. Broad and narrow line emission may come from different regions, such that some of these regions are obscured in some cases and not in other cases, and so on. So there are many different ways that we could be looking at the same objects and see very different results in our observations. And that is what the AGN unification model attempts to try to explain. And this is it. So the first thing we assume is that we have a supermassive black hole in the center. Around that, we have a thick disk and torus, which is close to the AGN, and okay, we also have the accretion disk itself. The accretion disk is where the actual emission and accretion is happening. Then we have a thick absorbing disk or torus close to the supermassive black hole. We then have here, but actually also out here, so this figure might be potentially a little bit misleading, but we have these very close into it, these broad line regions, which are photoionized by continuum emission from the accretion disk of the AGN itself. These broadline regions get very, very hot and very, very highly ionized. So that is where you see the emission lines from very highly ionized gas. And because they are so hot, you also see very broad lines because of a very high velocity dispersion in these gas clouds. The size of these regions is about a few light days to a few light months. And the electron density is about 10 to the 9 electrons per cubic centimeter. Compared to Earth's atmosphere, that is nothing, of course, but compared to your typical ISM region, this is extremely dense. Moving on to a little bit further out, where we have some clouds that are a little bit further away from the central accretion disk. These are therefore not as highly ionized and they are not as hot. They are more modestly photoionized and they show narrower emission lines. So these regions are 10 to 100 parsecs, so much larger than the broadline regions. And the electron density is correspondingly much larger, between a factor 1,000 and a factor of 1,000,000 less dense than the broadline regions. But 10 to the 6 is still quite dense compared to your typical ISM region. 10 to the 3 is more typical for the ISM in a galaxy in general. Then we have the dusty disk, the dusty torus, which will absorb a lot of the radiation that comes through it, but it is not covering in all direction. It is exactly a torus or a disk, not a completely surrounding envelope. And once we have this in place, we can suddenly begin to explain a lot of the diversity in our observations of AGN in terms of this model, which is what this drawing here is doing for us. What we need to know, however, is that it is not only a matter of viewing angle, but also of intrinsic differences. So for each of these 4 quarters, we have different intrinsic properties of the source, but the viewing angle differences you can see are very similar. So as you can see here, below here we have radio quiet objects, and up here we have radio loud objects. On this scale here, on the left, we have relatively low power sources, and on the right side, we have relatively high power sources. But much of the viewing angle effects that we see are still the same independently of the intrinsic property of the source. So for example, if we have a low viewing angle and we have a low power source, this is when we see a Seyfert type 2 galaxy. It is basically dominated by the galaxy because we cannot see the central emission, the central accretion disk, the central nucleus, because it is obscured by the torus. We can also not see the broadline regions. These are also obscured by the torus. So the only thing we can really see apart from the galaxy itself are the narrow line regions. Similarly, if it is radio loud, we can see a Seyfert galaxy with radio emission, which is called a narrow line radio galaxy. On the other hand, if we have a more steep viewing angle closer to phase on, we can see that we can actually have directly unhindered view down the barrel to the central nucleus, which means that we can suddenly see way more continuum emission, and we can also see down to the broadline region. And this is where we have Seyfert type 1 galaxies, as you saw from before, with the much steeper blue spectrum and the much broader emission lines, with the narrow emission lines on top of them coming still from the still visible narrow line regions as well. And the radio loud parallel to the Seyfert 1 galaxy is what we call the broadline radio galaxy. It is basically a Seyfert 1 galaxy with added radio emission. And then if we happen to be looking straight down the barrel of a radio loud galaxy, which has a jet, we can see this as what we call a blazar. We have a almost completely unhindered view down into the central continuum source and broadline region. We also see the narrow line region, but on top of that, we will also get blazed by this jet that will be pointing straight in our direction, and therefore make this object look even more extreme. Over here, we have basically the same phenomena as in the Seyfert 2 and the narrow line radio galaxies, but for a more high-powered source. This is what we would typically call a type 2 QSO or a type 2 quasar. And if we have a steeper viewing angle, we basically have the same kind of source here as we would have in the broadline radio galaxy or the Seyfert 1, but with a higher powered source. This will give us a type 1 QSO. So in that way, we are actually able to explain a very, very large part of the variation and the diversity we see in observations of AGN, in terms of this unification model, which can explain it in terms of a combination of intrinsic variation, as we see here, radio loud versus radio quiet, low power versus high power, and geometric effects coming from the viewing angle that we're looking at. Just a little bit for fun, we can take a look here at the imaging of an AGN core region in the galaxy NGC 4261. This galaxy has here been imaged with the ground-based optical and radio imaging. And as you can see, this is a huge structure. Here is the galaxy, which is an elliptical galaxy from the look of it, with these very strong, very bright radio lobes coming out in both ends. But then it is actually possible with the Hubble Space Telescope to zoom in sufficiently on the central regions of this to actually see the gas and dust disk or torus surrounding the central AGN on scales all the way down to around 400 light years, which I think, if you think about it, is immensely cool. That was it for part 1. Thank you for staying with me this far, and I will see you in the next one.